Here's the setup that we've got in this situation. I'll do the general setup and then we'll do the example of that function, the equation with the ln. We've got the function big F of all three variables, where we imagine that they're all free to vary. But secretly, we want to analyze the case where z is constrained to be equal to f of x and y. In other words, we're constrained to be on the surface. Here's the tree. Let's say w. Let's give a name to the output of f, because it's really important. Even though we're most interested in where the output doesn't vary, we want to, in principle, let it vary. We want to be able to walk off the surface in order to analyze how to stay on the surface. That's the cool thing, analogous to what we were doing in 2 dimensions. So w is a function big F of x, y, and z. So this is equal to w here. Then x depends on x and y in a really simple-minded way. Similarly for y. Z depends on x and y through the function little f. And that's what we eventually want to analyze. Okay, so let's write down the chain rule. And it's going to be a classic case where we're going to want to decorate it a bit more than it's usually decorated. Ooh, that's going to be an x. Okay. Let me just write down the simplest form here. Okay, so all the intermediate variables, x, y, and z, and then how they depend on x, because we're choosing, the idea was that we wanted to look at an x derivative. And we'll see right here, this, I claim, is the quantity we're really interested in. The original goal was to calculate partial z partial x for this function. It's really little f sub x that's going here. Okay, so the nice thing about this variable notation, the Leibniz notation, is it really accords with the tree well. But this is a very disturbing thing. It looks like these guys are the same quantity on both sides, and they're absolutely not. That's really a drawback of the notation, but you can fix that by putting evaluation bars everywhere. Okay, this is supposed to be how w depends on the final variable on the initial variables, bypassing the intermediates. So that we can denote that by saying, okay, going all the way down to this stage, it's only x and y that are variables. Z is not independently varying, and so this I'm going to decorate with saying, okay, only y is held constant. Really important that as x varies, that's going to change z on this side of the equation, because we're allowing z to depend on x and y. And so even though y is held constant, when x changes, z is going to change. And of course, x and y are directly going to affect w, and all these three things are going to affect it. Now here, this is just the top depending on the middle, so we'll denote that by saying, oh, okay, here, y and z are both held constant. I'm imagining here that I can change x, y, and z totally independently, and in particular, I can change x without changing y or z. That's moving straight forward off of the surface. This is just at the bottom level. That's just dx by dx, of course holding y constant, because x is just a function of x and y, and we're going to hold y constant. Similarly here for the middle level, that's y holding x and z constant. This is dy dx. Ooh, let's see, what was it again? On this bottom level, x and y are the only variables, and if I'm taking the partial derivative with respect to x, then I'm holding y constant. Oh, that's interesting. It's going to give us a very simple answer in a minute. Okay, here again, this is derivative with respect to z. Let me give myself a little more room. With x and y held constant. That is how w would depend on z if I could go straight up, which I'm probably not going to be able to do and stay on the surface, but it's going to be important for the analysis. And then dz by dx with y held constant. So all these guys are just with y held constant. These guys are with the other two of the intermediate variables held constant. It looks very complicated, but it's the same idea as we had in the previous case, where we have these two different perspectives. One is where x and y and z are free to vary independently of each other. I do not have to stay on the surface. And I look at how w depends on those guys, and that's these three. And then there's the recognition that really x, y, and z have a dependence on just x and y. And of course, the only interesting dependence is z depending on x. So this is what we'd like to isolate. Well, what do we have? dx by dx, that's definitely going to be 1. Okay, the rate of change of x with respect to x is 1. The rate of change of y with respect to x when y is held constant, that goes to 0. So that just goes away completely. That's the sense in which the y coordinate is really coming along for the ride here. Notice that none of the derivatives now are with respect to y. Okay, it's just not material because that wasn't what I was interested in. I was holding y constant, and it's really the x that I want to vary. Okay, so now dw dx. Remember, this perspective, when I'm looking at the whole tree, the w as a function of just x and y, letting z vary, That's staying on the surface, and the whole point was that big F was constant on that surface, and so this is just equal to 0. Okay, so now let me just simplify it. Plus dw, and you get very, very similar thing. And we're going to be able to solve that for this guy. Okay. So we get a very similar equation. I think I'll erase it all, except for the bottom. Okay. And we get the partial derivative that we care about that tells me how z varies when I vary x and not varying y, when I stay on the surface. Again, this crucial minus sign, dw dx, in the kind of fantasy world where I let x, y, and z completely vary, the three-dimensional perspective, over dw dz, that's this guy, again in the three-dimensional perspective. And if you wanted to say a little bit more concisely, big F, remember big F was explicitly just talking about the top two layers of the tree. The big F perspective is where I absolutely declare x, y, and z to be completely independent of each other. I don't care that there's this function little f that might theoretically link them. I really don't care. And so this is a little bit more succinct notation that automatically is supposed to include this information. This is kind of nice, though, to really remind yourself exactly what's going on. Because the big F, sometimes you can forget what layers of the tree that it looked like. I guess trees don't have layers. I guess onions and parfaits have layers, and ogres. But anyway, what levels of the tree, let's say that. Okay, so let's look at, oh, and again, with this notation, you can almost convince yourself that you could just do it by canceling fractions. The dw's cancel, the dz flips up, but the negative, you're never going to find it that way. Okay, so let's look at the example. Big F of x, y, z equals yz minus ln of x plus z. It's an x. Okay, I think I'll be able to do this without the thing running out on me. Okay, big F sub x, or dw sub x with y and z held constant, is just looking at this formula, doing the ordinary partial derivative in the usual way. And that doesn't have an x in it, so it's minus 1 over, because the ln turns into 1 over, x plus z, and I don't get any interesting sort of ordinary chain rule terms. Okay, oh, I don't need an equals there. Fz, okay, that's going to be y minus, oh, basically the same thing. Again, the chain rule would just be 1. Okay, and up here, let me just shoehorn it in up here. Okay, so that's going to be 1 over x plus z, with the minus sign canceled. Okay, and then over y minus 1 over x plus z. Okay, and I can do a little common denominator and canceling here. Multiply both top and bottom by x plus z, basically. And that's going to be 1 over the quantity x plus z, y minus 1. Okay, so that's going to be our general formula for the slope of the tangent plane to this guy. So again, I didn't graph a particularly accurate, well, I didn't even try to do an accurate graph, okay? But that's going to be, at any given point x, y, z, if I look at the tangent plane, that's going to be exactly how much it slopes positively or negatively in the x direction. Not a bad formula, and much, much, much easier than just staring at that algebra that you couldn't do to solve for z in terms of x and y and just throwing up your hands. Okay, that's a good place to stop.